Okay, so these are some problems that we did in class for linear kinematics. So we're going to start with the very first one right here. All right, we're going to run through these, showing you exactly how to use some of these equations to solve said problems. All right, so first is we're going to develop a reference system, and then we're going to write our knowns, and then write our unknowns, and then solve the best way that we know how. All right, so what is the acceleration of a runner who is running at a velocity of 10.3 meters per second and coming to a stop? So this person is running, so we can say our reference system is someone is running in the x direction, positive x direction here. Our knowns, we have a runner, velocity. So our v of I, our initial velocity here, is going to be 10.3. We have a t, which is going to be 4 seconds. And what we want to know is the acceleration. That's what we want to know. So we go up to our equations over here. And throughout this list, we're going to look for what we have, what we don't have, and what we need. It needs to be in that equation, if possible, using only one. So we have acceleration, we have time, v of f, and v of I, v of f. Now, next thing is we have our information from here, but what else can we infer from the question, which would be the final velocity, which is coming to a stop. And so we can actually say that infer that's 0. So we plug this equation in. We're going to start with v of f, so v of I plus at. Final velocity is going to be 0, initial velocity is 10.3. And then we're going to add the acceleration, which is what we need to know, and t, which is 4. So we bring this equation over here, 10.3. And when we minus subtract that out, we can move around 4 underneath. And then we come up with this for a. So 10.3 divided by 4 is 2.575, but then again, you need to make sure that you have a direction on here, negative 2.575. We can round this in this class, negative 258 meters per second squared. So due to our reference system, this is going to be going in this direction here. If this is positive and this is negative, so the acceleration is backwards from the initial velocity direction. Okay. Our next one here. So we have a football player. A football player accelerates 2.3 meters a second for 2 seconds when they are already running at 4 meters a second. What is their final velocity? And excuse any of this, the blurring is trying to focus on my pen here. So what we're going to do is we're going to set our reference system. Again, we're going to start with an x direction being positive in this. We were only doing linear kinematic problems here, one dimension. So that's all you have to worry about. Our knowns, acceleration 2.3 meters per second squared for 2 seconds. We have time 2 when they're already running at 4 meters per second. So v of I is going to be 4 meters per second squared here times seconds. Okay, so from this data, we're going to look at our kinematic equations over here. And we're going to use, let's see, we got v of 1. Oh, we also need final velocity as our unknown here. We need to know that. So final velocity, v of I, at, that's going to be using that same equation as before. Our v of f is equal to v of I plus at. Our v of f is what's unknown. We'll leave that as is, as our variable of interest. V of I, 4.0 plus a, which is 2.3 acceleration. And times t, which is 2. And so this equation can allow for initial velocity to be in the equation and then just acceleration of those other two factors. So for this, get our calculator back out. 4 plus 2.3 times 2, and that's going to be a V of F of equals 8.6 meters per second. Okay, next problem is a jumping problem, which is pretty traditional for biomechanics. And we have a person jumping from rest, so as they leave the floor, we're going to draw a figure right here. As this person is jumping and extending up, they're leaving with a y velocity, the y direction being positive up. That's our reference system. 4.2 meters a second. So initial velocity, 4.2 meters a second. Now that's all we have on this equation, this problem statement. So we're going to also think about what else is going on. So what do we need to do? We need to find the apex. Apex, which is the jump height. So you can take the, if the person's legs are straight up, the apex of the jump, the person's going to jump, it's going to stop, and then they're going to come falling back down. So at the point when they reach the highest point, velocity, which starts out at 4.2 meters a second, is going to stall out to be 0. So we can say the final velocity is 0 meters per second. Now also, when we're working with the y direction, we can automatically assume that we're on Earth, and our acceleration is gravity, which is 9.81 meters per second squared. So now we're starting to fill in some of these different variables, and we can look at our equations over here and find one that suits our needs. So we could use these two, but we need t here as well to kind of solve for. We'll be able to get t from this equation, but that means we weren't given t here, and then we could plug in t into here and to here, and we'd able to get that distance. So this distance right here is in one direction. So as you jump up and stall out and stop, this is what this direction is for. This time right here, as v of f becomes 0, it's in that one direction, it stops, so you only have that distance or that time it takes to get to that distance. So that's a good equation to use if you need to figure out the time. And then if you want what's the flight time, you could use our other equation that's given in the other sheet, or you can find t here and multiply that by 2, up and back. Whenever you have someone jumping off of a platform into somewhere lower or somewhere higher, then you're going to need to use two different equations for this. One, and you break it into two parts. One to go up, and then another equation to go down at the different height. Okay, but let's continue on here. All right, so the easiest thing to do is actually use this last equation here that already has final velocity, initial velocity a, and we want to find that d. Since we have three of those variables, there's only one unknown. So v of f, the equation here is v of v squared, v of I squared, plus 2ad. All right, so we just fill these in. This is 0. We have v of I for 0.2 squared plus 2a, which is negative 9.81, and your unknown d. So we can bring this to the other side, negative 4.2 squared, and then we divide that side by 2, negative 9.81, to get d. So we can plug that into the calculator there. The negative value, of course, is going to be taken out of the equation. So there's 4.2 squared. We're going to divide that by 2 and divide that again by 9.81. Okay, so that leaves us with d is equal to 0.899, which rounds to 0.9 meters. So they're jumping pretty high for this theoretical question. Okay. The last problem is here, and this is the change in position of an outfielder is from 34 now dash 90, which this would be in x and y coordinates, 3490 to 5590 meters in 10 seconds. What is their average velocity? Okay, for this one, we need to find the change in position first, and then we have our seconds, and we divide by seconds just using v equals d over t. Now, we have 90 both in the y direction, so there's no change there. So we're really only concerned with the x direction. Now, if you had a different coordinate, if you had 100 here and a 90 here, you'd have to subtract the end result minus the beginning, like we're about to do with the x direction. And then you do the x minus the final x versus the initial x. And then you use the Pythagorean theorem to get the hypotenuse of that. And that hypotenuse would be your distance there. But for this problem, it's a little more simplified. And so we're going to use x and a reference system right here. X is in the positive direction, and y is up here in the positive direction there. So x is equal to x of final minus x of initial, which if you place it underneath, 55 minus 34, which is 21. So our position, and that's going to be our distance. That's going to be our distance there, 21 meters. So then we take our distance, 21 meters, over 10 seconds, as we did in this equation here. There's your time, there's your distance traveled, and you're going to get 2.1 meters per second. Moving on to part B. What is their acceleration if they start from rest and we assume their acceleration is constant? Well, that's the whole definition of these equations, is we're holding acceleration constant. So starting from rest, we're going to say velocity initial is 0. And they're moving 21 meters. I like to kind of draw these out a little bit. And we have a final velocity here. We know that our average velocity is 2.1 meters a second. And we go over that for 10 seconds. Okay, so what do we know? What do we know? We know v of I is 0. We don't know what vf is, but we know what the average is, and those are not the same. We know that time is 10 seconds. And so let's see what we can find. So let's go back to our equations. We have a distance. We wanted to know the acceleration. So distance, we know the initial velocity, 1/2, we know the time. Okay, it looks like this equation, this one's going to work really well for us. All right. So our equation, d, v of I of t, plus 1/2 a t squared. All right, so d, 21, v of I of t, that's going to go out to 0 because that's 0 there, and t is 10 seconds. But it's 0 times 10, 0, plus 1/2 acceleration, and then time. So we got 10 squared. All right. So then we bring this over and get a on one side. So 21 times 2 divided by 100. And multiply that out. 21 times 2 divided by 100 is going to be 0.42. 0.42 meters per second squared. All right, that's all the questions that we're going to cover for this time.